And I'm going to turn this over to Ms. McGaw.
Okay, all right. So I'm going to try to share my screen. Let's see if I can do it. And there. And is that working now? Do you guys see my screen?
Something's happening. There you go. It's focusing now.
Hey, all right. So in this first session, this is nothing new to you. I don't think this is all review, completely review today. But if there is anything that I say or do that you don't understand, like Mr. Akampora said, please just like unmute and just say, hey, stop. What are you doing? Or use those little, you got those little icons at the bottom and somebody will be watching the chat. So feel free to do that because I don't want to lose anybody. And what we're talking about today are reactions and net ionic equations kind of especially. And that's, is it a lot of points on your AP Chem exam? Probably not a lot of points, but there's a lot of understanding that goes into this. And so that's one thing that I want you to be able to have as you go through this day. So in the AP Chem exam, I know in Chem 1, you probably talked about 5 types of chemical reactions. And I mean, those types are still there, but really in the AP world, we're just going to classify our reactions into one of 3 categories. They're going to be acid-base, oxidation reduction, or precipitation. And as we go through this session today, we're going to kind of like focus in on each one of those, and they could be classified in more than one way. Basic steps, just in case you don't remember, when you write a reaction, you are in charge of knowing what happens with that reaction. So sometimes you actually have to predict the products. And when you predict products, always, if you're predicting, you have to make sure that you balance with subscripts before you ever go to balancing with coefficients. And so you just got to make sure you go in that order or things are not going to balance. So the first poll question right here, which is conserved in a chemical reaction? Anybody want to try that question? Lou's got the poll up. What's conserved? So just choose an answer really quick. We don't even need 90 seconds for this. These are not going to be long multiple choice. Usually you get 90 seconds for multiple choice. I have 1 vote, 2 votes, a couple more votes. The questions
These
today
polls are anonymous, so you know.
Yeah, they're all anonymous.
Know,
Nobody's going to know
guess.
anything. So we can end that poll and share those results, and let's see how we look. Oh, I was stopped. I didn't mean to stop sharing.
I'll handle the polling.
Okay, sorry, Lou.
That's
so
okay.
Sharing the results. Let's look at that. So if we're talking about a reaction, what is balanced, what's conserved? Conserved means has to be the same on both sides, the reactant side and the product side. And so let me just go back to one of these other equations right up here and let's just look if moles are conserved or molecules are conserved. Let's say, for example, let's look at that oxidation reduction reaction. So I'm gonna I gotta move my pole out of the way and you can move your pole out of the way.
Oh, we can get rid of it, I think. We know what it looks like.
So let's look at this reaction right here. How many moles of reactant do you have in this oxidation reduction reaction right here? How many moles? Count the coefficients. There's 1 zinc. There are 2 HCl's. So on the reactant side, I have 3 moles, which would also turn into 3 molecules, right? So if I were talking about molecules, I could interpret an equation in more than one way. So I could have 2 molecules in an atom, all right? So if I look on the product side, how many moles do you have? You guys feel free to just like chat it in, open up your mic and just talk. It would be cool like that.
Emma says 2.
All right, and Emma, I agree with you, there are 2. So are the moles conserved? And that's a balanced equation, would you agree? I have 1 zinc, 2 H's, 2 H's, 2 Cl's, 2 Cl's. So choice B was your favored choice, and moles are not necessarily conserved. I mean, they could be. Like if you look at this first reaction, all the coefficients are 1, 1, 1, 1, and so we have 2 moles on the reactant, 2 moles on the product, but that's just by chance. It's not necessarily true. So the only thing that's really conserved, and I don't know if we have any, we don't even have any volume here because I don't have anything with gases.
Oh, you do. The middle one has a gas.
Oh, yes, I do have a gas. Sorry, Lou, didn't see that gas right there. So yeah, volume is also not conserved.
And Lisa, if I can interrupt here, because I know where this is going to go, but counting moles in this case is also a little bit disingenuous, since while we might have 1 mole of HCl, because it's a strong acid, it would actually represent 2 moles of particles in aqueous solution, and
True.
the same on the product side. So, counting moles gets a little bit trickier when you have dissolved ionic compounds or strong acids. But you're right, moles, and my examples, if I cut a brownie in half, well, now I've got 2 brownies, but I still have, I have a different number of brownies, but I still have the same amount of stuff.
Yeah,
chocolatey goodness.
So the only thing that really is conserved is choice A, mass and charge. So mass means like number of atoms and grams, and then charge, when we get into net ionic equations, that's the one that students most often miss on their AP exam. So I wanted to just kind of like point that one out there. So I hope anybody have any questions about that before we move away from that question. Does that make sense to everybody if you did not choose choice A? So I'm going to kind of go quickly through these first slides, if that's okay. On this slide, what I wanted to point out is I really like the idea that you can see all three representations. Here's a macroscopic view. What we actually would see in the laboratory, which many of you hadn't had a lot of lab experience this semester or this year, or even maybe a whole year. Maybe you haven't had a lot. So the macroscopic view is what we see in the laboratory, a colorless, clear solution. And then we have a yellow solution that's clear. And then we form another solution and it's clear at the top, but it turned kind of reddish brown and fluffy or something at the bottom. So we made a precipitate. So that's the macroscopic view that we would see if we were performing the lab in the laboratory. But there's also an atomic level. And on the AP exam, we don't usually ask you to tell me about the atomic level. We use the word particulate level. So if anybody asks you about a particulate picture, and you will see many probably on your exam this year, we're asking what's really in the beaker. So when I'm talking about this solution right here, if this was a silver nitrate solution, and it is, what's really in that beaker is I have silver ions floating around, I have nitrate ions floating around, and then they're surrounded by a lot of water molecules in a correct orientation. So that goes into IMFs, right, with ion dipole. And then I'm looking at this other solution, sodium chromate. So I have some sodium ions, those are just spectating. I have chromate ions floating around. But when I put those two solutions together, what happens is I see a solid form, and the representation of the solid is where you see a very tightly knit, kind of compact, really regular organization of all those little ions that were floating around. Now they're not floating around. They've made a solid, an ionic solid. And so that particulate representation, you should be able to represent reactions and recognize reactions in that kind of format. And then the symbolic level, this is the one that you've done since Chem 1. So in the symbolic level, we're actually looking at a balanced chemical equation, or a net ionic, a total ionic, or a net ionic equation. And we're going to go back through that because I know that's kind of hard. So that's kind of hard for everybody to do some of those net ionic equations. So let's look at those, all right? So a balanced equation, and I really hate the word balanced molecular equation, but that's what we always call it, even though you might have ionic compounds. We call it a balanced molecular. I just say balanced equation, a total balanced equation. So if I had something like this with copper 2 nitrate and sodium phosphate, it's all balanced. The complete ionic equation, I want you just to take a second and look at this, because I want you to notice what happens with subscripts and with coefficients, because that's the downfall, all right? That is the downfall. A coefficient in math class goes through a whole compound, right? And it does with a complete ionic equation, just the same. So this 3 multiplies through, and I get 3 copper 2 plus. The charge is very important. If you leave off your charge, I'm going to leave off your points. Polyatomic ions, do you have to memorize them for the test? Well, essentially, yes, because you have to recognize them. So right here in this compound, nitrate's a polyatomic ion. So that subscript stays with the nitrate, and its charge is -1. The little subscript out here, the 2, that's going to multiply by the 3, and I'm going to get 6 nitrates. When I come to sodium over here, that's a balancing subscript, and so that multiplies by the coefficient, whereas the 4 on the phosphate does not multiply. It just I have 2 PO4 groups. That's the hard part, I think, for most students. So what can you ionize in one of these reactions? Only strong electrolytes. So strong acids, strong bases, and soluble salts. And you have to memorize the strong acids. Nobody's going to give you a list. So you have to memorize those. Those have to be in your brain. So if you don't know them, learn them, all right? The strong bases are metal ions with hydroxide ions. They have to be soluble in order to be considered a strong base for a net ionic equation, all right? So in order to be considered a strong base and be able to separate 100%, they have to be soluble. So you have to look at those solubility rules. And then soluble salts, all nitrates and acetates. These are ones you have to memorize, all group 1 and ammonium. So what does it mean to be a strong electrolyte? It will light a bulb up really, really brightly. And the reason why it lights that bulb? Well, because if you go back to that particulate picture we looked at a minute ago, you would see all those ions floating around in the beaker. And with all those ions floating around in the beaker, there's a way for charge to move through the solution. And so that's why the one on the left is a strong electrolyte. This one on the right is probably a weak electrolyte. Maybe it's something like acetic acid vinegar. It doesn't ionize 100%. Maybe you guys are in acid base right now. And so here are some representations of some electrolytes and some non-electrolytes. Ones that are very, very weak. Because like over here in this first picture, you see one thing is ionized out of all of those particles. And I'm sure there's probably many, many more particles. We kind of oversimplify when we do these particulate pictures. But then you see something like sodium hydroxide, 100%. That's what we're talking about when we say strong. We want 100% of those things to be ionized. So if you look at this little pole right here, could anybody identify which of these would not be a strong electrolyte? Do we kind of have a good sense about electrolytes?
Fortunately, there's no E on this one, or E is not the right answer because I seem to have left off E.
Oh, I put a whole bunch of 5 choices because I figured if you do 5 choices, you can do 4.
I got most of those.
Okay.
E is not the right answer.
E is not the right answer. It's a nitrate. So all nitrates are soluble, right? All nitrates are completely soluble. One more vote really quick.
Okay, we're up to 6 participants. So we should be seeing, and all of you again.
Oh, awesome. Welcome, everybody.
I saw that you haven't learned this yet, and that's okay. Take a guess anyway, and a lot of this comes into, recognizing what kind of compound it is, and one of those might stand out for you. It's very difficult to, the presenters and I have had multiple years of practice. So we look at compounds and formulas very, they're familiar to us, but I know it takes a lot of practice to get that way. It's kind of like learning a language. And when you're starting to learn French, which I was never good at, I'd have to parse every single word. And obviously, if you speak French fluently, you can just hear an entire sentence and know what it means.
Yeah.
So we've got 4 of 6 people participating. I'm going to go ahead and stop the polling here.
All right, so let's check it out, guys. And like Lou said, yeah, you have to analyze every single thing, and nobody chose choice A. It is a strong electrolyte. You just saw that. That was a strong acid. So you recognize that. It starts with a hydrogen. That recognizes as most of the time an acid, and that's a strong acid. That's on our list that we memorize. And then if you look at choice B says sodium bromide. It's not an acid. It's not a base. It's a salt. So when you have a metal ion with a non-metal ion, we call those salts. And salts are ionic compounds, and ionic compounds are typically considered strong electrolytes if they're soluble, all right? So they're considered strong if they're soluble. What does dissolve? Dissolves 100%. So that would also be a strong electrolyte. Potassium hydroxide. So anybody in group 1, so I could even look at these 2 things right here and say anything that's in group 1 will always be completely soluble. If they're completely soluble, they're a strong electrolyte. KOH is considered a strong electrolyte. It's a strong base. It's a metal with hydroxide. So a metal with hydroxide makes a base. And so you should recognize those as bases. Like Lou said, this one is not the correct answer. It's a nitrate. All nitrates are completely soluble. So this is also a salt, and it would ionize 100%. So the one that would not be a strong electrolyte would be CH3OH. It's super tricky. Okay, that's super tricky because you're looking at it and it has an OH, C has an OH, but this is not a metal. This is CH3. So when I look at CH3, I have this compound like this, functional group with an O. And so this hydrogen is not going to be available. It looks like a hydroxide group to you. It's actually an alcohol group. How would you know that? You wouldn't really know that, but what you will know is that CH3 is not a metal. So these are all non-metals. So this is a covalent compound, and covalent compounds do not ionize in solution to any extent. All right. So that's how you kind of recognize that. So that is sort of tricky. That might have been back in unit 2 when you were talking about compounds. All right. Questions about that before we move on? And feel free, like if you are just coming in, so if you are one person who just has come in, we're open in our mics. We're a small group, so you can totally open your mic and just talk. It's all good. So you want to try one more of those? Which can be identified as a strong electrolyte. So not a not question, which one, and this is like a tier stem question. You'll not see any questions like this on your AP exam where you have to choose more than one choice, like Roman numeral 1, 2, 3, 4, but I love them. I love them.
And then on the poll, they could choose as many as they care to. So.
Oh, cool. Thanks.
I left off the A, B, C, D, and E, and just select any of those that you think might be a strong electrolyte.
Okay. Choose as many as you want to choose. A couple more votes. Come on, guys, it's fun. Don't you think this is fun? Nobody knows who's answering what. It's all anonymous. Your teacher will not know. And this is Saturday, and I appreciate you coming on a Saturday morning, getting out of bed on a cold day. So we just want to learn chemistry, and I love chemistry, so it's all good. Good.
All right, that's 90 seconds there. So let's go ahead and.
So let's check it out. It looks like 4 out of 5 think that H2SO4 is a strong electrolyte. Can anybody tell me what H2SO4 is? Can we identify it? You can just type it in the chat, unmute yourself with the space bar.
Sulfuric acid.
Okay, that is sulfuric acid. So that is an acid. Is it a strong acid? You bet it is. Okay, that's a strong acid. So a strong acid will be a strong electrolyte. So if you chose that one, you are correct. So sodium bisulfite, you recognize sodium ion is in group 1. This is a polyatomic ion. So yes, everybody who voted, this is correct. This is a soluble salt. Okay, a soluble salt. What is H2CO3? Did I hear somebody say?
Nobody yet.
You might find it in a soda.
Still nobody.
Have you ever heard of carbonic acid? So that carbonic acid is in your soft drink, but is that on your list of strong acids? If you go back and look at your handout and look at the list of strong acids, is that on your list? It is not. So this is a weak acid. And so this one would not be a strong electrolyte. Ammonium nitrate, all you have to do is recognize nitrate and you know that that's going to be a soluble salt. And so that one is going to also be. So the best answer would have been choice D if Lou had put them out. It's 1, 2, and 4. 1, 2, and 4 would be the strong electrolytes. So you guys probably have to do a little bit more practice on that, because that's really, we've got to recognize that if we're going to write a net ionic equation. All right. So we'll keep looking at that as we go through the session. We'll see some more. I'm going to go ahead and skip the one that will not dissolve in water. That's just not a strong electrolyte. And I'm going to put just choice B. Just circle it on your paper for you. How about which one's not a strong acid? Does anybody know which one's not a strong acid? Can anybody just like open up and say that? Or yeah, this should take you 5 seconds. Which of these that I've listed is not a strong acid? What?
Kind of a tricky one here.
It is a tricky one, but you have notes. So you go back in your notes and you look at your notes and see which one. And the more you look at it and you look at it, then you're going to go, oh yes, I get it. So which one is not on your list of strong acids? I was trying to be super tricky.
At their list. Because they're all going for HClO4.
I see it.
All right,
let's close that. So it looks like 3 people voted on that one, and all 3 of you chose HClO4. If I go back and look at my list, I'm going too fast. Looking at my list. Where is my list? Oh, there it was right there. Is HClO4 on that list? It is. Perchloric acid is on the list, but who is not on the list? It's tricky because it's with the same family. Look, HCl, HBr, and HI. HF is not on the list. This is a weak acid. So HF is a weak acid, and it's a really common one for students to miss. That's why I put it in there. I was just trying to trick you, and it worked. And thank you for like cooperating with me, tricking you on a Saturday morning. All right. Just kidding. I don't ever want to really just be tricking you. So let's look at some net ionic equations. All right. But for being successful with net ionic equations, we do have to know the strong acids, the strong bases, and the soluble salts. We have to recognize our polyatomic ions. We also have to recognize phases. So anything that is solid or liquid or gas will not be shown as ionized. So only aqueous solutions of strong acids, strong bases, and soluble salts, all right? And in this first problem, it didn't tell us, so I'm gonna say aqueous solutions. I noticed that whenever I was going through. So let's say we have aqueous solutions of potassium hydroxide reacting with nitric acid. So first we have to write formulas. They're not given to me, so I have to write a formula. Potassium hydroxide is OH. Nitric acid is HNO3. Somebody got that a second ago. You named it out. And so this looks like just a plain double replacement reaction, which in essence, though, we're going to name it another thing because we only have 3 categories. We recognize this as a base. We recognize this as an acid. So we would call this one an acid-base neutralization reaction. And when you put an acid plus a base, you end up with a salt plus water. And so this acid is going to donate a proton. That's what an acid is. It's a proton donor. So I end up with the water molecule, or HOH. How, if you wanted to write it that way, that would be perfectly fine. And then you end up with a salt, KNO3. And all nitrates are soluble, so I can put aqueous right there. So the next thing I would want to do if I were doing this on my own is I would check all the charges. So I would go to my periodic table. Potassium is a +1. Hydroxide memorized is a -1. Hydrogen +1, nitrate -1. Well, that means if everybody is +1 and -1 on the reactant side, there's still +1 and -1 on the product side because it's just a double kind of replacement reaction, acid base. So I don't really have to go through that process on the product side. And so I have a balanced equation. It's balanced with, I'm going to get rid of these now because on your exam, if you leave up, it's not erasing. There it goes. I did. Okay. All right. So now it's erasing. So yeah, so I would want to leave a balanced equation without any charges because if you leave charges, we think you think it's an ion. So the complete ionic equation, we have a K plus, an OH minus, an H plus, a nitrate. Water is a liquid, so we don't separate anything that's a liquid. That's a molecular compound, and they do not ionize to any extent in solution. And then potassium and nitrate. And then what you do is you get rid of anything that looks exactly the same on both sides. So the potassium ion looks exactly the same. The nitrate ion looks exactly the same. And so we're left with OH minus, H plus, producing H2O liquid. And so that is the net ionic equation. And really for any strong acid and strong base, this will be the net ionic equation. So if you can recognize all the way from this point down to here, you don't even have to show me the middle points if on the AP exam I'm asking for the net ionic equation of KOH with HNO3. Any strong acid, any strong base will give me that same net ionic equation. That would be a really handy thing to know for like multiple choice kind of questions, because I can see that could be multiple choice. So why don't you take a second, see if you can write this one down on your paper, see if you can do a net ionic equation. Take just a second and see if you could write those formulas. Could anybody tell me what is the symbol for sodium? You can just type it in, or you can open up your mic and tell me. What's the symbol for sodium? I don't see the chat. So John, would you be watching the chat? Na, thank you. All right, thank you. What about sulfate? It ends in an ATE, must be a polyatomic ion. Okay, Ethan, what's sulfate? Okay. Sodium is Na. What about sulfate? Does anybody know sulfate's symbol? Polyatomic.
SO4, but don't charge.
Okay, SO4 plus, and then what about lead? It's a weird one because it's one of those, you know, from the Latin. It's not L. It's a weird one. Comes from plumbus. Does anybody know lead symbol? On the periodic table you get for the AP exam, there are no names. So you do kind of sort of have to know these guys. Does anybody know lead, John?
Yeah, Polio does. So does
PB? Okay. Thank you. What about nitrate? We've seen that already today. Good.
They're not putting the charge in.
All right, that's perfect. John's saying he's complaining because you're not putting charges in, but that's okay. I mean, if we look at this, I can write it just like that. Then
I think Lisa was just asking for the atomic symbols, not the formulas or the charges, John. So be a little bit.
He's not very nice, Lou. Sometimes
I know.
like he's so picky. But we
I
just
will
need
say,
this much, right?
there's a special place in hell for AP chemistry students who omit charges from ions. So.
But it looks like a double replacement reaction again, and it is the double replacement reaction again. So you're just going to switch the first two partners. So you're going to end up with PbSO4, and then you're going to end up with NaNO3. And so we know that this nitrate's going to be soluble because it's a nitrate. And then lead to sulfate, it actually is going to be a solid. So this is a reaction that we're going to call a precipitation reaction. We're forming a solid, like the first picture that I showed you this morning, a solid from two solutions. And so that's going to be a precipitation reaction. Now we are not finished with this because, like John said, we didn't give charges. And so this reaction is not balanced. And so I would have to go back and I'd have to say sodium's in group 1, so it's +1. SO4 has a 2- charge. And I know that because I just saw H2SO4, right? I saw H2SO4. So this sulfate is a 2-. So I would need a subscript of 2 right by that sodium, Na2SO4. Lead says it's a Roman numeral 2. So that means lead is a 2+. You know, nitrate's a -1. John said somebody said that. So I put the whole thing in parentheses and put a subscript 2. And then we look and see if our equation is balanced, and it's not. I would need a coefficient in front of sodium nitrate to balance out the whole thing. So now I've predicted my products, I did my subscripts, I did my coefficients, and then we would be ready to go on and try to do our net ionic equation. Any questions about that? How you kind of figure that out? Or is that pretty okay? So then if we try our net ionic equation, the subscript 2 is going to come out as a coefficient. And I do have to put my charge here, all right? 2 sodium ions, because it's thinking about what is floating around in my beaker. Well, if I have a soluble salt, I'm going to have these Na pluses, 2 of them. I'm going to have a sulfate ion. And so I'm going to put this sulfate ion, I'm representing what's floating around in the beaker. And then for lead nitrate, I'm going to have Pb2 plus. I'm going to have 2 NO3 minuses floating around. So I'm going to write it like that. I have 2 nitrates floating around in my beaker. And then what happens is when I put all that together, the lead ties up with the sulfate. So the lead and the sulfate are going to come down to the bottom of the beaker and make a solid. My solid's not so organized, but that's my solid lead sulfate. And I'm going to leave that together because it is a solid. And then what's still floating around in my beaker are all my spectator ions. So I'm going to have 2 Na plus and 2 NO3 minus. And so those are my spectators, the NO3 minus, the Na plus. So my net ionic equation is just going to be lead plus sulfate, forming lead sulfate, lead 2 sulfate. And that's really the power of these net ionic equations. When you write one, you actually see what is going on in the beaker. And so it's really powerful because I know exactly what's happening here when I look at this net ionic equation. The sodium ions aren't really doing anything. Nitrate ions they're there because they're balancing all the charge, and that's how I got them in the solution. But the only thing that's really happening is the lead ions and the sulfate ions. That's where all the action is. And so that's pretty cool, I think. Do you think that's cool? That's a net ionic equation. We're going to see some more of those in multiple choice in just a few minutes. All right. So quickly through acid-base reactions, how do you recognize one? Recognizing acid-base reactions is really that memorization of what acids look like. So you've got acids. Acids are proton donors. What's a proton? It's just an H plus. So a proton donor and a Bronsted-Lowry base is a proton acceptor. And that's what I'm looking for. And if I ever ask you that question on the AP exam, that's what I want you to tell me back. It's an acid-base reaction. How do you know? How do I know? As I see a proton being donated or I see a proton being accepted. And so if you look at acetic acid, we recognize that as a weak acid. This is the conjugate base of that weak acid. What happened is this proton was donated, so the acid lost that hydrogen. Water picked up that hydrogen. Water went from H2 to H3, so water is acting like a base right here. And then this is my conjugate acid. So whenever I'm asking you about it, how do you know it's an acid-base reaction, that's really kind of what I would like for you to show me. I would like for you to show me that a proton is being transferred. So NH3 to NH4, this must be a base because NH3 went to NH4. It grabbed 1 extra proton. Water in this case is acting like an acid because water went from H2 to just 1. All right. So it's acting like an acid. And I'm making up new words this morning. So that's an acid-base reaction. You will recognize them. They should look something like that. So acid plus base gives me a salt plus water. We call them neutralization reactions, but that's kind of a misnomer. And you're going to learn that when you get to acid bases in a little bit. And when you get to that equivalence point, that means that the moles of acid equal the moles of base, and that's all stoichiometry. So you've already probably dealt with that one too. I'm going to kind of skip through the titration. You're going to get back to those. If you look, and here's another molecular equation with a net ionic, looks really funky. So I wanted to kind of point that out to you, because really this is just that same acetic acid, but this is written in the organic kind of way. So you actually, this still is an acid-base reaction. It's just that we have a basic salt over here. Baking soda and vinegar, you guys can do this when we get off today. When you do baking soda and vinegar, you actually see a gas being formed. And so that gas being formed is the driving force for that reaction. And so we're making a molecular compound. So this is also an acid-base reaction, because what really, if you were to write it, you would have written something like H2CO3, that carbonic acid. But carbonic acid quickly decomposes into CO2 and H2O. You don't even see it because you see the gas formed automatically right away. And so that's kind of how that one looks. And then redox reactions. If I'm flying too fast, you guys stop and ask questions, all right? Because I am kind of flying, because I want to get to some of those questions at the end of this. So if it's an oxidation reduction reaction, what you're looking for here is you are looking for somebody to change their charge. So this is one where the charges don't stay the same. When I have an acid base or I have a precipitation reaction, no element, no species changes charge. But when I'm looking at a redox reaction, we have charges that change. And what I mean by charges, I'm talking about oxidation numbers. So how do you identify these reactions? What I do is I look for an element in its free state, and that will get most of these reactions. It won't get all of them, but it'll get most of them. So if you see an element all by itself, then it probably, well, it is going to be an oxidation reduction reaction. When it's oxidized, you lose electrons. When you reduce, you gain electrons. And you might see reactions represented like this. And you may have already balanced with half reactions. You'll probably do it again. So if I have copper ions in solution that turn into copper solid, what I'm really, really focused on is that this copper has a charge of 2, while this copper that's a piece of metal is a charge of 0. So if I go from 2 to 0, that number is reduced. And so this is a reduction half reaction for copper. Copper actually gains 2 electrons. It's on the reactant side, so it's gaining. So this is my reduction equation. And so we're going to look at a couple of those. In order to figure that out, sometimes you have to figure out what the charge is. So can anybody remember how to figure out charges? So set this whole thing equal to -2 and see if you can find the charge of chromium. Go to your periodic table to find the charge of oxygen, and then just do a little bit of math and see if you can figure out what the charge on chromium is in the dichromate ion. Oh, Lou, thanks. You named it.
Whoops. I think I've typed in a 3.6 instead of 3.5 on the poll, but
I see that.
that C should, I didn't just notice that.
All right, couple more, 3 more responses. Come on, come on, come on. In 5, 4, 3. All right, let's check it out. So we only had 4 votes. That's okay. I do like the 3 people who voted for choice D. So let's check that out just to make sure everybody's on the same page. Oxygen most often has a charge of -2. So -2 times 7 gives me -14. So I'm multiplying the charge times the subscript, and it should be equal to the charge on the overall. So what would make that a true statement? That would have to be a +12. But you have 2 chromiums, so 12 divided by 2 would give me +6. So I just work backwards. Sometimes you have to do that to figure out what the charge change is in one of these reactions. So that's kind of a basic idea to figure out redox reactions. So here's another reaction right here asking who's oxidized and who's reduced. So can you figure out who's oxidized and who's reduced in this reaction right here? So what I want you to do is go through, identify the charges, and then you have to decide who, and the easiest one to do is who's reduced, because reduced is actually reduced on a number line. It looks like it's reduced on a number line. Electrons are negative, so when you gain minus charges, then the number goes down. One vote. Keep it coming. Okay, Lou, let's call it. All right, so the majority say that choice A is the answer. All right, so let's go through and just check this out. Majority does not always win. All right, but let's check this out. So what I'm going to do first is I'm going to give a 0 to these elements in their free state. That's the easiest thing for me to do because I can see them. And then I'm going to go back and I'm going to figure out anybody else. So let's go over here to magnesium chloride. Well, we know Cl is in group 7 or 17, whichever way you're talking about it in your group. It's a halide, and those all have a -1 charge. This whole formula should balance out to 0 because there is no charge in the upper right-hand corner. It's not an ion. -1 times 2 is -2. So that means magnesium must be a +2. Then we'll do the same thing over here for iron 3 chloride. So the equal to 0, -1. So the iron must be a +3. So what's going on here? We have iron going from +3 to 0, and we have magnesium going from 0 to +2. So which one is actually going down in charge is the one that's reduced. So this one is reduced, +3 to 0. Going 0 to +2 is going up in charge. That means I'm losing electrons. So this is my oxidation. And now I'm going to see if I can find an answer that has iron 3 and magnesium with a 0. So do you see an iron 3 with a magnesium as a 0? I do. I see it right here. So what's being oxidized and what's being reduced? Oh, okay. I guess if you chose that one or you chose C, I would, yeah, either one. The way it's written, I guess, is actually who's oxidized. So that would be magnesium. So I guess choice C is the best choice for the order of that. I don't think the AP exam would ever do that to you, so I apologize. So yeah, we would not give you two choices that would just be like this. I don't believe we would do that. That wouldn't be fair, would it, Lou? That would not be fair.
No, we would never do that. They would never do that.
Yeah, they would never do that on the exam. So yeah, the way it was written, oxidized, then reduced, but yeah, order doesn't matter. As long as you got those two and that makes sense, I think that looks good. All right. So how about this one? How about this one? You've got 5 different equations. And we've got 2 questions here. So Lou, you put this all in one poll for both questions, right? And so they'll just,
yeah, so students should answer both questions.
Okay, yeah, you can just scroll up and down. I've never done 2 at one time. That's awesome.
I'm pretty good, huh?
You are pretty good. I didn't even know you could do that.
I can.
I'm always lazy with my polls. I always say just A, B, C, D, E, like, and then just relaunch, relaunch, relaunch.
And for the first question, you can choose as many of those as you would like.
You can choose as many as you want for the first one. You are looking for oxidation reduction reactions.
And Zoom would not let me put subscripts or superscripts, so you'll have to kind of figure out the formulas from all the numbers are there.
I bet the kids are used to that because there's a lot of our software that doesn't recognize chemistry. It's really kind of ticks me off, right? So that's been 90 seconds. So you should have an answer at least for the first question. When you're practicing and you get some multiple choice back, even like from your teacher or whatever, and you get your test back, if you do get your test back, you should like sit and try to practice and time yourself. Give yourself only like 60 seconds for every multiple choice and see if you can do it in 60 seconds. So push yourself for time. That's one of the things that's really the hard, you know, you're having to do it in a super quick amount of time.
Kind of like doing interval training.
Yeah, just kind of like, because just like you practice for that, you have to practice for these AP exams because you get a little stressed and it gets kind of anxious. And so you're kind of worried about, oh my goodness. So let's go ahead and stop that one, Lou.
I've already done it.
Yeah.
And there are the results.
All right. So let's see. 5 out of 5 think that this is an oxidation reduction reaction. And I totally agree with you because you know what I see? I don't even have to do anything except for see that silver has 0. So I know it's a redox reaction because I have an element in its free state. Same thing happens down here with Roman numeral 4. So I know that Roman numeral 1 and Roman numeral 4, I know both of those are redox reactions. Then I have to kind of look at the others and see if I think anybody's changing charge. So I really would have to figure that out. In the sulfur trioxide, this is -2. The hydrogen is +6. So that would give me +6. In the H2SO4, that which was the question down here. All right, what's the sulfur in the H2SO4? 2 ways to figure it out. I like to just look at SO4 2- and set the whole thing equal to -2. And then I've got -8. So that must be a +6. So this sulfur is +6 up here. And this one is +6 on the second answer choice. So I've got that. That means that, you know what? This is not a redox reaction. I recognize Roman numeral 3 as an acid-base reaction. It is not a redox reaction. It's acid-base. And so I know that that's not going to happen. And then I look at this 5th one. And again, it looks kind of funny, but it's a carbonate. So that's a salt. And then I make this carbonic acid like I showed you before. And so this is also not a redox reaction. Nobody is changing charge. So it should just be the first one and the 4th one for redox reactions. And it looks like that's about how you guys chose. So that was really, really good. That's hard, but that's one of the things we would expect you to be able to do kind of on the fly, figuring that out. And then a particulate picture again. So you have the macroscopic view, the like particulate view, and then a balanced equation right below. So you kind of see what's going on. And I really do want you to focus in on how, look at this particulate view. If it's a piece of magnesium ribbon, it's a very organized solid. Oxygen gas, diatomic, you would be looking for that. And we would expect you to draw that if you were going to draw oxygen gas. And then here, magnesium oxide, the oxygen comes and lays on top of that magnesium ribbon and it turns white and chalky, but it's a solid. All right, it's a solid. So that's kind of what a particulate view might look. And another particulate view, potassium as a metal, and then chlorine as a gas, another diatomic, and then another solid, potassium chloride. And then active metals, those will all be oxidation reduction reactions. In Chem 1, you may have learned an activity series of metals. On the AP exam, we're not going to give you an activity series of metals and you don't need to memorize it. If we give you a reaction, it should happen. So you wouldn't have to think about that. But if I take a metal and it gets replaced, like in this picture, we have lithium. I wish we could do this in lab anymore. It's so fun. But put lithium metal into water. The lithium metal is a solid. Water, you should know the structure of that. And then what happens is when you put an active metal, like anybody in group 1 with water, you get a base. So you make a base and hydrogen gas, and that base is going to be a strong base. So that's a super tricky net ionic equation too, because the lithium can't ionize, the water can't ionize because it's a liquid, but the lithium hydroxide would ionize into 2 Li plus and 2 OH minus, and then you have hydrogen, which doesn't ionize. So that looks like a funky, like net ionic equation. So that looks kind of funny, but notice the particulate pictures. Displacing a metal by another metal, like copper making silver. So I put a piece of copper wire down into some silver nitrate. So the silver nitrate, you see it floating around. I don't see the nitrate in this picture anywhere, but what happens is copper actually leaves the surface. So copper is leaving the surface, going into solution, and you see that because the solution turns from colorless to blue. You don't have to know colors of solutions either, but it's really kind of cool. And then what happens over here is you see the silver atoms laying on top of the copper atoms. So they're being reduced. They're going from +1, Ag plus an electron going to Ag solid, while copper is going from copper solid to copper ions and 2 electrons. And you probably already did those reactions, those half reactions when you were doing unit 4, because that's kind of in that unit, but that's pretty cool, right? And so now what I have for you for the last couple of slides and for the last few minutes, not too many minutes, we're going to do just a couple more questions, all right? Just a few more questions. So what about this one? Now, this is another memorized kind of thing, but you've seen some of these reactions already this morning, all right? You've seen some of these reactions already this morning. I don't know how I got away from my screen. Right there.
There it is.
So one of the products is an oxygen gas. And again, you can choose as many as you would like. Choose as many as you would like. So this category is not actually one of our 3 categories, but are you responsible for doing something that's not acid base or redox? Oh, wait, these may be the same thing. Decomposition, synthesis reactions, yes, those are still tested on the exam, even though they may not look like they fit into one of your categories.
Let's stop it there.
Yeah, cool. All right, so let's check it out. We got all kinds of answers, and I agree with choice D too. So if I'm going to decompose mercury oxide, I'm going to end up with mercury and oxygen gas. I'm not going to balance these out all, guys. Hydrogen peroxide, does anybody know what that one decomposes into? This is in the brown bottle at your house. It's just water and oxygen gas. That's why it's stored in that brown bottle. It'll react with light to produce that oxygen and is turned into water after a while. Chlorates, metal chlorates will also turn into KCl. They'll turn into the metal chloride and oxygen gas. But anything that's a carbonate, when I decompose that carbonate, I'm going to get a different gas. I'm going to get calcium oxide, which is lime, but I'm going to get carbon dioxide. So the only one that's not going to produce oxygen would be calcium carbonate. That's carbonates, recognize that those make CO2. That's a kind of an important idea. And so it says, what type of reaction does this? That doesn't really fit here actually, because these are decomposition, and most all of these that produce oxygen, I guess it does fit. These are all redox reactions, all right? They're all redox reactions. The only one that's not is choice A, but redox reactions, look at this oxygen all by itself. It's a 0, it's a 0. So it's a 0. All right. So those are redox reactions.
And let me interrupt for just a second to tie things together. Many of you, or some of you may have covered the ideas in Unit 9, but for most of these, because you're producing a gas, when you heat something up, this is going to be an entropy-driven reaction. So many things will decompose on heating, and usually that's because we're forming a gas, which means that we're going to have a increase in entropy. And since the temperature times delta S term will then dominate the delta H term, many things decompose at high temperatures. Sorry,
Gas-
Lisa, I just want to throw that
yeah.
out there to make some connections there.
Yeah, perfect. So if you don't have any questions, let's move on to another one. So precipitation reactions characteristics, we already saw it in the picture. So solutions form a solid. Solutions form a solid. So what if we tried to do a net ionic equation between silver carbonate and hydrochloric acid? And I will start you off with a balanced formula for silver carbonate, Ag2CO3 plus HCl. And silver carbonate is not very soluble, so it's going to look like that. All right, so I'm going to start you off. Can you finish out that equation and give me the net ionic equation? It's only one answer choice this time. Okay, only one of those answer choices this time. And then choose the type of reaction. So again, two things are going on here. And I only have 2 minutes. Okay, Lou?
We're going to stop now. And it's a little tricky because there are a couple of things going on, and you don't see that very often, but it does happen.
Yeah. So when you have silver carbonate and hydrochloric acid, again, you're thinking, oh, this is just a double replacement reaction. Let's finish it out. So we would make AgCl. And we know silver chloride, or we might not know, but you got to know. All right. Halides are all soluble except with silver, lead, and mercury. So silver chloride, and then we have H2CO3, but wait a minute ago we said if we saw that H2CO3, I showed you that picture and it doesn't really do that. Every time I have a carbonate with an acid, it's going to bubble, and the bubbles are going to be carbon dioxide gas and water. So once I get this, if I were doing this as a multiple choice question, I'm going to write out my basic equation, and then look, I can eliminate this choice and I can eliminate this choice. And now I'm down to 3. So I'm down to A, B, or C. So then I say, okay, well, wait a minute. If I have a solid and I have a solid over here, we know solids cannot, they can't ionize. So the only answer choice possible is choice A. And you want to get kind of good at that when you're thinking. You want to be able to go through this as quickly as you can and not really have to do the whole net ionic equation if you don't have to do that. So if it was a multiple choice, and this reaction is kind of tricky, I guess I would say. I would call it a precipitation reaction, I guess, because I do have a solid formed on the product side. This solid carbonate will completely react with hydrochloric acid.
Well, I think a good argument can be made for also an acid-base reaction, because the hydrogen ion and the carbonate ion, that really is a neutralization.
Correct. So I think, yeah. So it could even be this one too. Yeah.
So we should have been choose all that apply for the second part of that. Lisa, we're right at 11 o'clock. Thank you so much. Let's take a break here. I'm going to pause the recording now and welcome everyone back, and turn the mic over to John Gelder.
Okay, just
Or I thought I was. Whoa.
Sorry.
I've got to mute Lisa.
All right.
So
Lisa needed to mute herself.
I apologize.
And I'm going to share my desktop via AirPlay. In a moment. There we go. All right. So you can all see, we're going to do some thermochemistry today. Thermochemistry is a topic that is very frequently on the AP exam. Probably most recently, we might have seen it more in the free response than in the multiple choice. But if it's not in the free response, it will be in the multiple choice. And so I want to talk a little bit about what we're going to do. We're going to maybe learn some vocabulary this morning, and I think I'll change that color to maybe blue, because red is red. We don't like red. So we want to gain some intuition about heat, mass, and change in temperature. And what I thought I would do in the first portion of this presentation is we would do a couple of thought experiments to come up with a relationship between heat, mass, and change in temperature. So we're going to do that by considering a few questions. And so here is our first question that I'm going to look for an answer of right or left, and these are pertaining to the beaker that you see above. Here's the left beaker, and here's the right beaker.
Now I put it on the poll as left to right, John, because
there's a bunch of writing on the in this question, and this is one of the things you have to be prepared for on the AP exam, is that there will be a lot of words that you will have to plow through in order to answer either a multiple choice or a free response type question. So while I'm babbling, it's like everybody is answering the question. Many of you are answering the question anyway.
And John,
so,
Professor?
I will. So Lou, I think got
so.
this.
And I'm just going to say that
You guys
90% of the people would call that left or right instead of right or left at the bottom.
If we add the same amount of heat to both beakers, the beaker on the left is going to have the higher final temperature. So your intuition is doing very well so far. So what I'd like you to do then, when we think about heat, which has the symbol Q, mass, the symbol M, and change in temperature, delta T, I would like us to think about what the relationship is in this particular experiment that we're doing. The Q, the amount of heat, is constant. I'd like to know what's the relationship between mass and change in temperature. Is it a direct relationship or an inverse relationship? And remember, we saw, you made the claim that the beaker with the smallest amount of liquid had the largest change in temperature. So
Okay, I've stopped.
so
We have our
you
poll
would be
here.
thinking that this was an inverse relationship. And the way we write that inverse relationship is we could say that mass is proportional to 1 over the change in temperature. So let's look at another experiment. Here, again, we have 2 beakers, and we are going to be, we have the same initial temperature. If the final temperature of both beakers is identical, is the greater amount of heat added to the beaker on the right or the beaker on the left? So this is the beaker on the right or the beaker on the left. Who gets the most heat? So that delta T is constant. Who gets the more heat?
And this might be familiar for those of you who cook a little bit and maybe make heat up coffee or heat up a cup of water for coffee versus heating up a
All right.
bowl of water for
We've
pasta.
got most of the responses at this point. So I agree, the beaker on the right is going to have the most heat added to get the same change in temperature. So mass and Q. So I'd like to know what's the relationship between mass and heat when delta T is constant in this problem. What's that relationship? Is it direct or is it inverse?
All right, so
Okay, so 3 of you agree that this is a direct relationship. We had to add the most heat to the beaker with the most water. So that kind of relationship is that mass is directly proportional to Q. Oops. Let me get rid of that. At when delta T is constant. And then we've got a few slides here. I'm going to sort of skip through them to get to the third. Well, let's see. We just did 2 experiments, one in which we kept the, let's see, that was delta T constant, and the other one was Q was constant. So we sort of had 2 experiments, and we saw that mass was inversely proportional to a change in temperature when Q was constant. And then we saw that mass was directly proportional to Q when delta T was constant. Anybody have an idea of what we'll keep constant in the next experiment? We kept Q constant, then we kept delta T constant. So if you're thinking mass, then you would be thinking correctly. So what we're going to do in this case is we're going to add twice the heat to the beaker on the right This gets 2Q, and this gets Q. And what we want to know is the beaker on the right or the left have the highest final temperature. So in this case, we've got mass constant. Yeah. So here, all right, I think that's a good response. We are seeing that with mass constant, that we agree it's going to be the beaker on the right that is going to receive them, will have the highest final temperature, so the highest delta T. So now the question becomes, how are Q and delta T related? Is that a direct relationship or an inverse relationship? Okay, I agree. Direct relationship. So we've now done these 3 experiments. I'm going to go ahead and write experiment 3 here, where we kept mass constant. And we saw that Q was directly proportional to delta T. And so these 3 relatively straightforward experiments sort of give us an overall picture of the relationships between these 3 variables: heat, mass, and change in temperature. So I'm going to jump forward quite a ways on our slides. And I'm sorry if this is driving everybody insane, but maybe I'll just go here. But heat is proportional directly to mass and to delta T, and mass and delta T are inversely proportional. So we can sort of write sort of a proportionality that heat is proportional to mass times change in temperature. And to get a proportionality to an equality, what we do is we just change it from a proportionality to an equality. We add a constant times this constant C times delta T. And C is something that's unique to the particular substance that we're interested in, but this is called a specific heat. And if we solve for C in just this mathematical relationship, C is equal to Q divided by mass times delta T. We can sort of see what the units are on C. Units on heat are joules. The units on mass are grams. And the units on delta T are degrees Celsius. So our specific heat has units of joules. So it's kind of compound units, joules per gram degrees Celsius, which can be kind of complicated. And this is a relationship, as we will see in a little bit, is on the AP equations page. And what have I written here? I've written danger, Will Robinson. We have to be very careful with this relationship, because while this relationship calculates the magnitude of the heat released or absorbed, it does not give us the sign of Q. And on the AP exam, we are most interested in being able to, we're most interested in the student demonstrating how to calculate the magnitude of the heat, and also to determine the sign, not so much the sign of Q, but the sign of delta H. And those are typically 2 points on the AP exam that are very frequent. that we see them all arising. So what I would like to do is to, I think what I'm going to do is sort of talk for just a moment about, we can use the relationship to calculate the magnitude of the heat, but how do we get the sign? And you may recall some experiments or some problems that you've encountered where you've mixed hot and cold water, or a hot piece of metal that's been added to water at room temperature, or you added an ionic solid to water and measured the temperature change of that dissolution process. And there's some others, mixing a strong acid with a strong base, or a strong acid with a reactive metal, or, as we'll look at here in a moment, a strong acid with a metal oxide. And the way we sort of figure out the sign is by using the first law of thermodynamics. That is, when I mix hot water and cold water, I know that whatever heat is lost by the hot water is going to be gained by the cold water. And that's what this relationship says right here. That I can't gain or lose any heat in this process, theoretically. And so the hot water, the Q of the hot water plus the Q of the cold water has got to equal 0. And so if I can write that kind of a mathematical relationship, I can then move the cold water over to the right side of the equation. And when I do that, I get a negative here. And so it's with this first law, the application of the first law of thermodynamics, that we can figure out the sign. We can use the relationship that Q is equal to mass times specific heat times delta T to calculate the magnitude of the heat, which is typically what we're asked to solve for. But it's the first law of thermodynamics that enables us to assign a negative for an exothermic process or a positive for an endothermic process. And we'll see that here in just a moment. And so let's go ahead and look at this first problem where we're going to consider the reaction between magnesium oxide and hydrogen ion to form magnesium ion and water. Notice that in the stem of the problem talks about hydrogen chloride, hydrochloric acid, aqueous HCl. And this is really an important connection that you have to be able to make. Lisa was just talking about HCl, and we know that HCl is a strong electrolyte. And so in the net ionic equation, which we are seeing here, the chloride ion has been canceled out. It's a spectator ion, and so we're not going to include it. It's not been included, but what has to happen for the AP student, the AP student has to make that connection that, oh, HCl here, it belongs to the H plus in the balanced chemical equation. So, so we have to think about making those kinds of connections in a lot of different kinds of problems that we encounter on the AP exam. Net ionic equations is very important, and so we have to be thinking about that constantly. So the first thing that we're seeing in this particular problem, we're looking at this reaction and we're told that the task is going to be to determine the enthalpy change for the reaction. So we're going to be interested in the delta H of reaction, which is an enthalpy change. And in this kind of a problem, we're going to have to find Q. And so we don't see it yet because we've got a couple of preliminary questions that we have to address. And one of those is in part A, which is the limiting reagent in all 4 trials, HCl or MgO, and justify your answer. So this is a two-headed coin, but we need to be able to justify our answer. And so one of the ways that we can approach this is to just look at this reaction and try to summarize all of this information. Because if we're doing stoichiometry and we're being asked to determine limiting reagents, we're interested in knowing how many moles of magnesium oxide we have and how many moles of hydrogen ion we have, because those are the reactants in this particular problem. And so we're falling back on stoichiometry, even though this is essentially a calorimetry type of problem. So we've got to calculate moles, and moles are worth points on the AP exam. And you'll notice that we're given the volume of the 1 molar HCl, and we're given the mass of magnesium oxide. So in this particular case, there might be points earned for determining moles for either or both of these 2 reactants. And on the AP exam, we have to be able to establish that we know how to calculate moles, and we have to communicate that to the reader. So if we think about, well, how do we get moles of the H plus? Well, we're given a concentration and a volume, and so moles of H plus are going to be determined by just taking the volume in liters times the molarity. This is 1 mole of HCl in 1 liter. And so that's going to come out to be 0.100 moles of H plus in this particular case. So here I've clearly showed to the reader how I figured out the moles of H plus. How do I get the moles of the MgO? Well, in this case, for the magnesium oxide, I need to figure out moles. And so our first mole is 0.25. So let's take, or the first number of grams is 0.25 grams of magnesium oxide. So I can convert that to moles. And 1 mole of magnesium oxide is about 24.3 for the molar mass of magnesium and 16 for oxygen. So it's about 40.3 grams. And so 40.3 divided into 0.25 is going to give us 0.00620 moles of magnesium oxide. So now I know I have 0.0062, at least in experiment 1, 0 moles of magnesium oxide and 1/10 of a mole of H plus. So anybody want to put in the chat who the limiting reagent has to be in this particular case?
John, we've already done the poll, and the results are pretty good.
Okay.
So that's our polling results.
Well, we might get one more. So I'm agreeing with the majority that the magnesium oxide will be the limiting reagent.
And John, can I
And this is
interrupt you for
pretty
just a
easy
second?
for us to sort of to see that, because if I've got 1/10 of a mole of H plus and I need half as many moles of magnesium oxide to react with that 1/10 of a mole, that's 0.05 moles. I don't have anywhere close to 0.05 moles of magnesium oxide. So magnesium oxide has to be my limiting reagent. So sort of setting up this kind of a reaction, and that 0.0062 moles of magnesium oxide are going to react, and 0.0124 moles of H plus are going to react. I can see that my final amounts, this is my initial, this is my change, and this is my final amount. I'm not going to have any moles of magnesium oxide remaining. So that is our limiting reagent. So, so that's
John,
kind
can
of
I
cool.
interrupt here at all?
So that answers our first question about the limiting reagent. In part B, I'm going to go down here to part B. We're told that one of the trials is inconsistent with the data on the other 3 trials. Identify the trial with inconsistent data and draw a line through the data for that trial in the table above. So what we have is we have to figure out one of these trials' data is inconsistent. And one of the scary things is, we'll note that all of the volumes of the HCl are identical. We've got different masses. Experiments 1 and 3 have 0.25 grams of magnesium oxide, and experiments 2 and 4 have 0.5 grams of magnesium oxide. 0.5 grams. And then every one of these have different initial temperatures, and well, I guess the last 2 have the same final temperature. But we look at all of that and we might feel overwhelmed. Recalling this particular problem on an AP exam when we scored it, that this was a real challenge for many students. However, when we think about this kind of data, we should be thinking about not the initial temperature, not the final temperature, but the change in temperature, the delta T. And if we think about this, all of this data, the volume and the mass of the magnesium oxide are fine the way they're written. But all of this data can get reduced down to just the delta T. And if we look at the data, delta T is always T final minus T initial. And so for trial 1, we can see T final minus T initial is 1 degree Celsius. In trial 2, 29.1 minus 25 is 4.1 degrees Celsius. Trial 3, 28.1 minus 26 is 2.1 degrees Celsius. And trial 4, the change in temperature is 28.1 minus 24.1. We're back to 4.1 degrees Celsius. So when we think of simplifying the initial and final temperatures, which all have sort of different numbers associated with them, all of a sudden we get a little bit easier source of information to maybe help us. So maybe with that, could you predict which of the trials has is inconsistent with the other three trials. Okay, we've got three responses so far, and 4 responses. And so, yeah, trial 2 or I'm sorry, trial 3 or trial 1, those are sort of the ones that we're kind of, suspect of. But in fact, it is trial 1, which is the inconsistent trial. Notice in trial 3, the amount of magnesium oxide that reacted with the volume of HCl is half what it is for trials 2 and 4. And in both trial 2 and 4, we saw that 4-degree temperature change. So we're only having that limiting reagent, magnesium oxide, so we would expect the delta T to be half also, but not a fourth. We would not expect having the magnesium oxide to cause the temperature change to fall by a factor of 4. So, so it is trial 1 and not trial 3 that is going to be our best choice for inconsistent. So, so let's then look at where we're going to need to go after that particular question. So now in part C, we can see it says for part C and D, use the data from one of the other 3 trials. So you can see I've already marked out trial 1. And we're going to assume the calorimeter has a negligible heat capacity and the specific heat of the contents of the calorimeter are 4.18 joules per gram degree Celsius. So that's a specific heat. And assume the density of the HCl is 1 gram per milliliter. So those kind of assumptions are going to simplify our figuring out the magnitude, calculate the magnitude of Q when magnesium oxide was added to 1 molar HCl. Include units with your answer. So here we're being asked to calculate Q, and we remember that we are given this relationship on the AP exam, this one that we had developed with those 3 experiments, that mass times specific heat times delta T. And notice we got delta T. Remember, delta T was 4.1 degrees Celsius for experiment 2, 2.1 degrees Celsius for experiment 3, and 4.1 degrees Celsius for experiment 4. And you recall in our previous, well, whatever. So we've got our delta T for whichever experiment we're going to use. We've got the specific heat that was told to us to assume it was this. Now we've got to figure out our mass. And notice we've got a volume of HCl, and we're told the density of HCl, this 1 molar solution, is 1 gram per milliliter. So if we've got 100 milliliters with that kind of a density, we know that we've got 100 grams of the HCl. But this mass, we have to realize, has to be the mass of the solution. And so that's going to be the mass of the HCl and the mass of the magnesium oxide, whichever experiment we're going to use. So in calculating Q, if we go ahead and use experiment 3, for example, that's going to be 100.25 grams times 4.18 joules per gram degrees Celsius times 2.1 degrees Celsius. And we'll notice that our degrees Celsius cancel, our grams cancel, and so our answer down here is going to be in units of joules. And for this particular case, I think our answer comes out to be about, that we are going to calculate a value of about 1.72 times 10 to the third joules for this particular, for experiment 3. So we've calculated a magnitude, 1.723 times 10 to the third. That's the magnitude.
John?
And we've included the units in our answer, joules. And so it's really, really very important. I know your teachers are always reminding everyone about being sure that your numbers are accompanied with units. And so that's very important on the AP exam, particularly in a case like this, because that could be a point for having the units and then a point for the magnitude. And then finally, determine the student's experimental value of delta H for the reaction between magnesium and hydrochloric acid. So I'm going to move down to this slide to determine the student's experimental value of delta H. Well, we recall that delta H has units of kilojoules or joules per mole. And so in this case, per mole of reaction, we were told. And so what we have to do is figure out how do we calculate this delta H, because we have a number of steps that we're going to have to worry about. We've got Q. We know that our value of Q was 1.72 times 10 to the third joules. So there's our joules. Moles, well, I know some moles. I know how many moles, because magnesium oxide is our limiting reagent. I know how many moles are in 0.25 grams. That was our calculation of 0.0620 moles of magnesium oxide. However, we're supposed to calculate moles of reaction. And so that's the little tricky part in this particular calculation that we're doing, because I've got to get moles of magnesium canceled and moles of reaction replaced in the denominator. So the little secret to that is if we go back up to this balanced chemical equation and we say, oh, that's my reaction. And in my reaction, I've got 1 mole of magnesium oxide, 2 moles of H+, 1 mole of magnesium ion, and 1 mole of water. But I know how many moles of magnesium oxide reacted. I've got it right here. But I just need to do a conversion that 1 mole of magnesium oxide is equivalent to 1 mole of reaction. That is, if I make the claim that this reaction as written has 1 mole of magnesium oxide, that's per this mole of reaction, then my moles of magnesium cancel. And, oh, 880 joules. Oops. I did look at the wrong trial. Okay, so Dr. Akampura has said that I've got, yeah, well, that's, what's happening? Why aren't I erasing? I got it. So instead of 1.72 times 10 to the third, 1720, it's actually 860, 800, thank you, 880 joules for trial 3. Right, 880 joules. In trials 2, this would have been 1720 or 1760. 1720 joules. So I apologize for that.
But thanks for catching.
Yes, thank you. Thank you, Lou, for catching that. All right, so when I do this division, I should get a number that's equal to 1.39 times 10 to the 5th joules per mole of reaction. And since delta H is typically kilojoules, I can convert this to kilojoules when I remember that 1,000 joules is 1 kilojoule. And don't make the mistake that many students do on the AP exam and make the claim that there's 1,000 kilojoules in 1 joule. So this will come out to be 1.39 times 10 to the 2nd kilojoules per mole of reaction. Okay, so this is our delta H, but now we've got to also realize that this was an exothermic reaction. That is, the Q of the reaction is going to equal minus Q of the solution. And so this number right here, our Q of solution, that needs to be a negative number, so that when we end up with our delta H calculation, we come up with a negative value for our delta H because heat is being released. Notice that our temperature has increased in all 4 of our experiments. And so we have to watch out for that. We calculate the magnitude with the equation Q equals mass times specific heat times delta T. But we don't get the sign from that equation. We get the sign from the realization that the Q of the reaction is minus Q of the solution. So here was our Q of solution. We have to have a negative. That gives us a negative for our delta H. And that's our application of the first law. And many students will calculate the magnitude correctly, but not calculate the delta H with the correct sign. And so that's something we have to watch out for doing these kinds of heat, Q equals mass times specific heat times delta T, and then calculating our delta H.
And John?
Now, I'm going to jump down to here because now we still have this same reaction, only now we're given some enthalpies of formation for these 4 substances, and we are asked to determine the accepted value of delta H for this reaction between magnesium oxide and HCl. And so when we think about, oh, okay, how am I going to do this from delta H of formation? That's when we want to take advantage of looking at the equation page for the AP exam, which I've got down here for that section of thermodynamics and electrochemistry. Here's our relationship between Q, mass, specific heat, and delta T. And then here is our relationship between delta H of the reaction and delta H of formation. Products minus delta H of formation of the reactants. And so what we can do up here is say, oh, okay, well, delta H of this reaction is going to equal to the summation of the delta H of formation of the products. Our products are magnesium ion, 2 plus, the delta H of formation, plus the delta H of formation for water, and minus the delta H of formation for the magnesium oxide, plus 2 times the delta H of formation for H plus. And so we're given all of the delta H values for all 4 of these species. And so what we need to be able to do is to be able to substitute those quantities properly from the data table that we're given in the above. And so delta H of formation of magnesium ion, that's minus 467 kilojoules per mole, plus the delta H formation for water, which is a minus 286 kilojoules per mole, minus the delta H of formation for magnesium oxide, which is a minus 602 kilojoules per mole, plus 2 times the delta H of formation for H plus, and that's 0 in this particular case. So here are our values. And this is a place where many students get confused because I've got minuses and a plus and a minus, and then a minus and a minus. So we just have to be careful when we're doing that particular, keeping track of those negatives. So let's sort of do this stepwise. And we see that if I were to add these 2 negative numbers, that's going to come out to be a negative 700 and I think 53 kilojoules per mole, minus a minus 602 kilojoules per mole. And so what we're going to end up doing is adding 602 kilojoules to a negative 753. And so that's going to come out to be a negative 151 kilojoules per mole for the delta H of this, the accepted value for this delta H of reaction. And when we go back up and look at our calculation above, we came up with this negative 139 kilojoules per mole. So we're a little bit off from the accepted value, and that's always been a source of error kind of question that frequently occur on the AP exam. And we can understand, you know, here we've got a more negative value. That is, the accepted value of our delta H of this reaction is more negative by about 20 calories, kilocalories, 139. So it's about 12. kilojoules per mole that were off. And the value that we had done from the data is less heat. So we lost some heat in this experiment, and more than likely that's going to be due to the little kind of calorimeter that was used in this experiment. They're not very good thermal insulators, and so some of the heat can get lost as we're doing that reaction, which would explain why our accepted value is more negative than our calculated, our observed value for the delta H of this reaction. So, so we're constantly, we want to be able to use our equation page to use the right equations. And what I'm going to do is I'm going to jump forward because there is one other problem that I think that we'll have time just to look at really quickly, which is another kind of common question on the AP exam that we see, and that's using bond energies to calculate delta H's of reactions. And with bond energies, it's kind of tricky, because if we were looking at that equation page, here's that equation page again. I've got a delta H of reaction, but that's based upon our delta H's of formation, not bond energies. And so we have to realize that there are mathematical equations that students are expected to know that are not on the AP equation page. And in this case, it's this equation, that the delta H of a reaction is equal to the summation of the bond energies of the reactants minus the bond energies of the products. And this can be confusing to students, because when we look at these equations for delta H, delta S, or delta G, it's always products minus reactants. And so we have to be sensitive to the fact that when bonds are formed, heat is released. So in the products, we're forming bonds, and so that's the negative that we have here for that heat released, while as when we break bonds in the reactants, that is a positive quantity. So when we come up and look at this kind of a reaction between fulminic acid and isocyanic acid, forming isocyanic acid, we have to think about bonds broken and bonds formed when we do this kind of a calculation. And so the way we can do that, delta H of reaction, remember it's the bond energies of the reactants. So we see that we've got an HC bond, a CN triple bond, and an NO single bond. And so here's our HC bond, here's our C triple bond N bond, and here's our NO bond. So we're interested in these numbers, 413 kilojoules per mole, plus 891 kilojoules per mole, plus 201 kilojoules per mole, minus the bonds of the products. And I'm going to use a different color, go back to blue. And here we've got a HN bond, and carbon-nitrogen double bond, and a carbon-oxygen double bond. So here's our HN bond, our carbon-nitrogen double bond, and our carbon-oxygen double bond. And so now we're going to subtract 391 kilojoules per mole plus the 615 kilojoules per mole plus the 745 kilojoules per mole And so when we do all that, we'll get an answer. And I'm just going to find my answer. And there it is, minus 246 kilojoules per mole for using bond energies. So the thing that we have to watch out for is the importance of that it's bonds broken minus bonds formed. So bonds broken are in the reactants and bonds formed are in the products. And so we see that in this particular case, the reaction comes out to be exothermic for that. So,
Thank you, John.
Right.
Can you hear me at all?
I'm thinking that we're, what's our status, Lou?
John, can you hear me?
Mr. Akampura?
Can you hear me? I don't think you can hear me.
Oh, I'm not hearing. Lou
Right.
either.
I think we're a little bit over time, so I think that's a good place to stop. So thank you very much. And thank you, students, for being part of this. This recording will be available. So I will talk with you
Is that
later.
something that we're doing? I'm gonna